So I totally did not forget to resume the recording in the class. So I'm just recording this video again to review all these slides. The exam logistics are that the exam is scheduled during your regular lab time. You're allowed one cheat sheet. I'd suggest having color pencils so it's easier to trace code. Carry your ASU ID and do not cheat, please. Okay, recursion. This is one of the most popular questions that a lot of students get wrong. So I'll review that first. You've seen these GIFs, right? This sort of infinite glitch or something. This is a function calling itself, right? And in CS programs, what we do is we harness this ability and then we kind of shape it to get the correct solutions. We stop it when we want to. And the way you do it is with decomposition and base case. So let's compute a factorial recursively to show you how it works inside. So let's try to compute factorial of 5, right? The first step is to decompose it. By decompose, I mean is perform some kind of operation that gets us closer to the base case, right? And now the compiler, what it's going to do is it's going to take this result and it's going to store it in a call stack. And we're going to focus on the smaller problem now. So we went from factorial of 5 to factorial of 4. And now we do it again, and then again, and then again, until we reach the base case. The base case here, factorial of 1, just computes to 1. So once the compiler gets to that base case, it starts popping these elements back from call stack. So once we get 1, it plugs it in 2 times factorial of 1. Then that result in 3 times factorial of 2, 4 times factorial of 3, and 5 times factorial of 4. After that, we get our final result. Okay. In exam, you might get questions that ask you to compute, to trace a recursive solution, or they might ask you to see what the iterative method does and just choose the option that's closest that gives the result in the recursive pattern. Running time. So this is a strange topic that a ton of students get wrong as well. Um, One thing I'd suggest is having this graph in your cheat sheet. No matter how well you are at runtime, we always tend to just mess up the order, right? Some questions might give you 3 of these runtimes and ask you what's in the middle. Some might ask you what's the best one out of these 3, stuff like that. And the way you read this graph is the closer it is to the y-axis, the worse the algorithm is. So I've put little GIFs here to show you progression from like happy to panicking. And just have it in the cheat sheet and you will be good. The way you compute runtime is, I'll demonstrate that in these word problems. So start with constant runtime, right? O of 1. And the word problem says, check if array square bracket 0 is even. And now the way you do it is you take the data structure that's being used in the problem and you try to expand or shrink it and see how that affects the process that we're trying to follow. So we have an array, we're using an array. So what we'll do is we'll take 10 elements, for example, and we'll perform this operation. So check if the first element is even. Well, we do that, that takes us one step. And now we'll take 100 elements and we'll repeat it. You see, there's no change in the steps you do. It still took us one single step to do it. So that's constant right there. We'll get to log n later on, but let's consider O of n, counting numbers. So if I ask you to compute, if I ask you to count up to 10, you'd start with 1, 2, 3, all the way to 10. But if I ask you to count up to 100, you'll take 100 steps now. So that's a 10-fold increase, right? 1, 2, 3, all the way to 100. So that's 10-fold increase. That's linear right there. N log n, alphabetizing a stack of papers. So imagine you have a stack of papers and you're taking all these papers out and piling them into separate 26 piles of each alphabet. And every iteration you do, your stack size reduces. So that reducing property is logarithmic, right? When you do the actual math on these processes, logarithm shows up. So You'll do all that in 310 and 450, but now you just have to trust that this reducing property is logarithmic in nature. N squared is just a pairwise operation on all users throughout all towards all the users on the platform and to find out the mutual friends of all users. So that's N squared right there because each user is being mapped to all the users in the platform, and those users themselves are mapped to all the users on the other end. There are three types of runtimes: worst case, average case, and best case. Best case is represented with omega, theta represents average case, and big O represents worst case. Okay. Let's do data structures, right? And I'll just talk about runtime as we go on through data structures and algorithms. Um, we get data structures because of how memory is structured, right? If you look at this grid here, all you need to understand is that memory is just a grid of ones and zeros. You'll understand why we got to that, how we got to that, and why all these addresses are prefixed with hex, OX. But the important thing to notice is it's a grid, right? And arrays are just a sequence of numbers um, that take up one cell each, and you get to a null character that represents the end of the array. So it's taking single cells. So that's something you need to see here, right? Stacks are kind of like arrays. They're last in, first out. That would mean the last element in is the first element out. There's two kinds of operations on stacks, push and pop. Push just pushes an element to the top, and pop just takes the element at the top. So it doesn't have any argument, but push does. And here's a little clean visual, right? If you try to push 100 on the current stack, 100 just sits on top. And if you try to pop, 100 is the first one out. So the last one in is the first one out. Same thing. The runtime here is constant because we don't care how big the stack is. The data structure we use here is just an array, but the amount of steps it takes for us to push and pop doesn't change with the size of the stack. So that's constant right there. Queues are first in, first out. So instead of having the last element come out, the first element in the queue is going to be the first one out. Think of it like a Starbucks queue or something, right? The first element that's in the queue is going to be served first. And if you were the last, you're just going to be at the end of queue and you'll wait until all the other elements in front of you are processed. Two kinds of operations, NQ and DQ. They're basically push and pop, but special names. They're constant as well because the amount of steps it takes us to enqueue, get in the line, and serve one, it doesn't change. We don't care what's in the middle. So they're both constant. Node. So one thing we noticed here is that stacks, queues, and arrays, they all had single cells. But in node, we're taking two at a time. So how does that help us? Um, Here's how we structure the nodes first, right? There's two pockets is what I like to call it. Or you can think of it as boxes. Each box just has one value and an address to the next box, and it goes on from there. And with this property, we get to build a new data structure called linked list. Linked list, you can make a new linked list just by creating one node and calling it head because special names. So in memory, this is what happens. Head of 98, right? That node, it's just got the head tag. So head is always accessible to us, but whatever's inside is just going to be accessed through references. So here's how we do it. We'll link new nodes to list. So we'll make new node and we'll link it with the dot next property. Once we do that, this happens in the memory. So the reference, the second node, is stored in the next pocket of the first node. And it goes on and on and on, right? And we'll use arrows for clarity. You don't have to know the references, just know that this is happening under the hood. And this is inserting a node at head. So this one's one of the popular questions. A lot of students get it wrong because what they forget to do is they forget to realize that order matters in linked list operations. So here's how we do it. Here's our linked list. Here's the new node. And what they do is they just link it. Head is equal to new node. But there's a big problem here, right? The next pocket was not filled here. And so we lost access to these nodes. So that's incorrect. And we lost access to the list. Here's how we should do it. Here's our new node, and what we'll do is we'll fill the next pocket first, which just means copying down the address of that the head's pointing at. So new node.next is equal to head, and then we just change the reference that's stored in head. So head is equal to new node, and now everything is connected, everything is perfect. So general rule of thumb, always start by filling the next pocket. But yeah, inserting a node at end. So we inserted a node at the first node at front, but let's try to do the same thing in middle somewhere. And the way you do it is you start filling the next pocket first, and then you change the reference before. It's just the same thing, but instead of head being passed around, you're passing head.next. The runtime, inserting it at the nth position takes us n steps, right? In an array of 100 elements, if we want to insert something at the 100th position, we'll have to take 100 steps. In a linked list of 1,000 elements, we take 1,000 steps to insert something. But inserting at head is just always constant. We don't care about the size of the linked list. We only care about what's at the front. So it's constant right there. Now we have completed linked list where we took two cells at a time and we just kind of connected them smartly and we got linked list. But what happens when you take three of them? We get three nodes, right? One to store the value, one to store the left reference, and one to store the right reference. So what we can do with these three nodes is we can build binary trees now. With two references, we can imagine it as trees. So these data structures, they're all zeros and ones in the memory, but we try to make it make sense to us by making these trees and these visual diagrams. There's two kinds of binary trees, complete and full. The way you find out if a binary tree is complete is by flattening it out. Flattening just means going level by level, left to right. So in this case, we got this sequence of numbers by going level by level. So 1, then 5 and 6, then 8 and 2, then 7 and 4. That's how we got the sequence of numbers. And that's a complete binary tree. I can say that because there are no empty cells between two numbers. And it's fine if you have empty cells at the end. A complete binary tree only cares about empty cells between two numbers. And let's say 2 was missing here. In this case, this is not a complete binary tree because when you flatten it out, there's an empty cell between 8 and 7, right? So that's not complete. Full binary trees, on the other hand, just have either 0 or 2 children at every node level, right? This is a full binary tree. This is a full binary tree. That's all you need to know. Traversals, these are very important. And over the past 2 years, every single exam has had traversals. So I'd suggest putting these down in the cheat sheet in order. So the in order goes left, parent, and then right. You can use self and parent interchangeably, that doesn't matter. And if the left child is it's a tree itself, then you just recursively call that traversal on that little tree. So here's what I mean, right? Um, the left child of 1 is itself a tree. So we just recursively call in order on that little tree, and now we can perform the traversal. So that's left, parent, and then right. So that's the left child done of our original problem. And now we can go to the self node of the bigger problem. And now we do the same thing on the right child. So that's left, self, and then right. And that's the right child done. And now the same thing goes with pre. Instead of it being left, self, and right, it's self, left, and right. So the same thing, self, left, recursively call it, and then we complete that traversal, and then the same thing on the right child. And now for the post, it's self, left, right, and self, left, right, self, and then self right there. So just put this here down on your cheat sheet. This and in the exam, all you have to do is just pattern match it, right? Just recursively call it on the children, and you can see how the recursive calls are done here. But yeah, this is really important. Put it on a cheat sheet. BSTs, one of the most popular questions that a lot of students get it wrong, and it's interesting. But BSTs have a special property. Every left node is less than or equal to the current node, and every right child has a value that's bigger than a current node. So in this case, every node that's on the left side of 6 has a value that's smaller than or equal to 6. And every node that's on the right side of 6 has a value that's bigger than 6. And you can see that pattern is followed on every single node. And that's an important feature, and we use this to perform binary search later on. And here's how you construct it from a sequence of numbers. So 6 is just a single node, so we do it. We just put it. Now 2 is up next. So we have to make a decision. If it's smaller than 6, which it is in this case, we just make it a left child. And then if a left child is occupied, just make the same decision on that child. So 1 is smaller than 6, but 2 is already occupied. So we'll just make that decision at 2. And 1 is smaller than 2, so it becomes a left child of 2. And this goes on and on. And we get our binary search trees. Okay. Searching algorithms. So up until now, these were just, one-liner kind of questions. The algorithms take a lot of time to understand and to trace, right? One of the most popular searching algorithms are linear search. This is the fundamental one that a lot of us just tend to do. Linear search just goes step by step until it finds the right node, the target node. So on worst case, we take n steps, right? If it's at the end, we take n steps. And this changes because in an array of 100, we take 100 steps, but in an array of 1,000, we take 1,000 steps to get to the last node. So that's linear right there. Best case, if the element we wanted to search is at the front, then it doesn't matter what size we have, it's constant. Theta, on average, the algorithm is still not that nice, so it's constant, it's linear. Binary search is one of the most efficient ones. The only assumption is that the array that we wanted to find an element in is sorted. So here's how the algorithm works. If the middle element is the target, we return the index and we quit. Else, we have to make a decision. If the target is bigger than the middle element, then we just repeat the search on the right half alone. We do not care what's on the left half. We just do it on the right half. And on and on and on. That's it until we find the element. So here's our array, and we'll try to find 8 here, right? The middle element is 5, and that's smaller than 8. So we'll take the right half, and then we'll repeat it. And then again, and we've found it. So it took us 3 steps to find 8 here. So we made log n comparisons, right? We had 9 elements, so it comes out to 3.17, and we did take 3 steps here. So that's the math checks out. The worst case is log n. Best case, if the element we wanted to find was in the middle, we don't care about the size, it's still in the middle, it's constant. On average, it takes log n. So it's much better than linear search. But yeah, sorting algorithms are, you don't have to know the quick sort, but there are a bunch of sorting algorithms we do cover. That's a quick sort, merge sort, heap sort, insertion sort, bubble sort, and selection sort, I believe. Quick sort, you don't have to know the working, but it'd be nice to have it. There's also a pseudocode in the study guide, and that's really important because a lot of variations of those pseudocode are asked in the exams normally in the past years that I've been assisting. The algorithm goes, if there we just have a single number, we quit, or we choose the last element as a pivot. We partition the rest of the elements into 2. So 1/2 is just going to have all the elements that are less than or equal to the pivot. And the right half is going to have all the elements that are greater than the pivot. And then we move the pivot in the middle, and then we sort the left and the right halves recursively. So here's the array that we wanted to sort. We'll choose the last element as the pivot. And we'll use two-pointer technique to partition them. You don't have to know the actual workings, but it'd be nice to just see the pattern and realize how we partition them. So the blue pointer's job is to pin the elements that are bigger than the pivot. And what red will do is it'll stop at the element that's smaller, and we'll just keep swapping it, right? So here's how we do it. 5 is bigger than 2, so we'll stop blue there, and we'll move red until we find one that's smaller than 2. In this case, we did. Once we fill both of these in, we swap these elements and then we continue. So blue moves ahead and it marks 5. Red moves ahead, but the moment the pointers cross, we have a condition. This is the base case, the recursion solution. The moment the pointers cross, we just swap. We just plug in the 2 in the middle. So that's how we do it. And now you can see partitioning is done. The left half has 1, which is smaller than 2, and the right half has all the numbers that are bigger than 2. And now we repeat it on the left half. It's a single number, so we quit. And then we sort the right half. So we choose 5 as pivot, and then we use the 2-pointer technique on these 3 elements. So we know that 4 belongs to the left side, right? And right there, that's the swapping done. The pointers crossed, we plug 5 in the middle. And then we do it again and then again. So that's the array sorted. Worst case, the algorithm takes n squared. Best case, n log n. On average, n log n. So it's a pretty good algorithm, right? N log n is not bad. Merge sort. You need to know the actual workings here, so pay attention to this. If you have a single element, you quit, else you sort the left half, you sort the right half, and then you merge. Here's how this works. We take the left half, and then we recursively call merge sort on that left half. And now that recursive call is going to split it into the left and the right halves again, and then again on this until we arrive at a single number. So now these 2 calls are quit, and now we get to the merge step. So the merge step simply compares the elements and then inserts them in order. So 1 is smaller than 5, so 1 and 5 go in that order. So the left half of the second level is done, and now we sort the right half. It's a single element, so we're done, and now we merge it again. Merge just means compare and then plug them in the right order. So 1, 3, and 5, and now we do the right half now. We get to the second level, then that's the merge, and that's the right half's right call. And now we merge again. And now this is the biggest merge, the outermost merge. Okay. So the number of merge calls is n minus 1. And the number of recursive calls to merge sort is 2n minus 1. The worst case time complexity is n log n, best case is n log n, and where average case is n log n as well. More sorting algorithms, heap sort, insertion sort, selection sort, and bubble sort. You don't have to know it. You just don't have to know it, but you do have to be aware of the runtimes. So I would suggest just putting these in the cheat sheet. So the worst case, the best case is here, and the average case. What next? I got a bunch of emails about students being stressed, so I prepared this slide with a bunch of stuff to do after the exam, and it helps because it takes off the stress away from this exam, right? The exam is not going to be that bad, right? 80% of it is just one-liner or like little code, little bits of code that you just have to look at the cheat sheet and just know how to do it, right? Just pattern match it. What you can do is you can build something cool. Odin Project has a lot of stuff for web development. You can watch a TV show. You can learn cybersecurity. We have enough knowledge base, so to actually kind of make sense in Punk College, start with the orange belt and go on from there. If you like algorithms, just do lead code, read a book, work on a project, build your own X repository, have some really cool ideas, and start planning for hackathons. You can make ASU pay for these hackathons as long as you apply early and if you plan to attend the right hackathons. Tree Hacks is definitely one of the best ones. They're hosted at Stanford, and a lot of Berkeley kids, Stanford kids, Harvard kids show up, and it's really big. And there are a lot of companies. You can talk to them, networking. You get the gist. Hack Texas is good. Hack GT, you get to go to Georgia Tech, which is really cool. And Hack MIT is personally the best organized, I believe. It's really well organized. You can also attend CTF events, capture the flag events. They pay a lot of money, and you just have to know memory stuff like that, hacking stuff. They have a bunch of resources there that you can go through the summer. And again, ASU does pay for travel, and there's the experiential grant. Just apply early and you'll get it. These are the mistakes that I made, and so don't make the same mistakes. Just, be smart about it. There's also one video that I prepared or like found it somewhere, and it shows you why runtime matters and why VCS people care a lot about runtime. Um, this here is 100 random elements, and we apply various sorting algorithms on these 100 to see which algorithms perform best. Quicksort, was n log n. So you can see quicksort and merge sort are already done. Shell sort, we don't have to know about it. We know that bubble sort is n squared, and selection sort is kind of n squared, and it falls in the middle. So you can see they're still slow, they're still working their way through. Insertion sort was slightly better than selection, but insertion is done. And insertion is done. Selection and bubble are still running because they're n squared. Selection is done, and bubble sort is the worst. It is n squared in every single area. You can watch the whole videos. There are other variations, like some semi-random stuff like that. But you can see how runtime affect the speed of the algorithms. But yeah, that's about it. Feel free to browse through the slides. Everything is available in Canvas. These slides will help you answer most of the questions in the exam. I've also have a bunch of problems that I've prepared. These are tougher than the normal exam problems, but I think that preparing for tougher problems will just help you solve a variety of other medium-ish problems. So there's a recursion problem, there's a tree traversal here. Mastery one's my favorite. But yeah, I've given all the solutions and these are in the announcements. But yeah, that's about it. Thank you so much.